Well, I'm very happy to introduce Professor Margherita Porcelli, because I think it's the very first time she's being introduced as because she's just been promoted. I'm very happy. Congratulations, Margherita. And so if you want to share your screen.
Yes. We cannot hear you very well from here.
Far from the laptop.
Probably. Yes.
Okay, so today Margherita is going to talk about a spectral palm algorithm for dictionary learning. Enjoy.
So thanks, Davide, for the introduction. And first of all, let me say that I'm very pleased to take part to this first meeting in the TOC4Deep project. And I really want to congratulate with you guys for having succeeded so far in the project proposal, but I'm sure that the outcomes will be very good as well. So congratulations again. I have maybe I have to wait, full screen. Wait, sorry, I cannot. Full screen. Can you see my screen? Yes, yes. So let me start. So the talk I'm going to present is a joint work with Valeria Simoncini and our former PhD student Domitilla Brandoni. So the focus of the talk would be the solution of dictionary learning problems. These problems became very popular in the last years because it can be used in several applications, and in particular in applications related to data science. And the reason is that dictionary learning is one of the leading sparsity promoting technique that can be used, for example, in image classification. Before introducing the problem, I just want to make a step backward and talk a little bit about image compression. So the basic principle behind image compression is that given an image that here I will denote by a vector in Rn, an image can be represented as a linear combination of basis images, so a set of n images in this case, through a set of coordinates, which are the components of this vector x in Rn in this way. Okay, so this basis expansion principle is the basis of many compression protocols. So, for example, in JPEG or JPEG 2000, where the basis of the images is fixed a priori. And for example, JPEG 2000 use wavelet transforms, or the JPEG protocol one use discrete cosine transforms, and so on. Of course, if the basis is known in advance, storing the image or storing the coefficients in the representation of y in the basis d1 dn is equivalent. So what's the advantages of representing an image as a combination of basis images? One has advantages if the basis is chosen in a clever way. So what do I mean by a good basis? A good basis is a basis that allows to pass from the image to its representation very fast. And of course, this is the basis of the algorithms for computing the discrete cosine transforms or wavelets. Another property of the, another desired property of the basis is that has to be sparse. Sparse means that an image can be represented by few elements of the basis. So sparse means that the vector x that is the representation of y in the basis D is sparse. Of course, a clear advantage of having a sparse representation means that one can save memory in storing x in place of y. So the hope is having a representation when only few elements of x are non-zero, or maybe only few elements are, I mean, many elements are quite very little, so that one can get rid of them, and so performing a sort of compression of the image. But another feature that comes out, for example, in image classification, is that sparsity is also useful because it helps in revealing structural information on the contents of the image. And we will see how this will be exploited in image classification. So the idea of dictionary learning is that of not using a fixed a priori basis to represent an image, but to learn the basis automatically from the data. This is because, for example, there are a set of images, for example, images with faces of people, which are not well represented, for example, using a wavelet basis. Well represented means that the representation is not sparse enough, it's not satisfactory. So the idea is that, for example, for this set of images, a tailored basis could be more effective. So if we want to follow this idea of learning the basis automatically from the data, we have to relax a bit the idea of basis. So the idea is that instead of using n vectors d as a basis, one use more than d. And this forms what we call a dictionary. So a dictionary is a collection of k images, which are called atoms in the dictionary learning literature, where k, so the number of atoms in general, is greater than or equal to n. So it is an overcomplete dictionary. And the reason for that is that in this way, an image can be represented in more than one way using that basis, and so one can hope to find a basis that gives also a sparse representation. Another requirement that is commonly done in this framework is that the atoms have the norm of the atoms is equal to 1. And this is useful also because in this way, the coefficients, the coefficients of the representations have a meaning. The magnitude of these coefficients have a meaning in the representation. So the task of the dictionary learning is the following. So given a collection of P images, the idea, the goal is to find the dictionary, that means K images, such that each image can be represented as a sparse linear combination of the atoms. Of course, as much as possible, and we will see what we mean. So if we write this problem in a matrix fashion, this is the problem. We have a matrix of data Y. So you may think to have in each column an image that has been reshaped as a column vector. So we have a given data matrix Y. So the idea is to find the dictionary that would be a matrix like this and a sparse matrix X, such that Y is approximated given by the product of D times X. So this is a sort of, this problem is corresponds to the computation of an approximate factorization of the matrix Y. And a distinctive feature of this problem is that all the matrices involved are fat. There are more columns than rows. Just want you to pay attention to the fact that while the number of rows and columns of Y are given by the data sets, and correspondingly the number of rows and columns of X, of course, the number of columns of D and the number of rows of X that here are denoted by K are an input parameter. We have to fix a priori this parameter, this problem dimension. And we will see that these things has an impact then in the problem formulation. So here, just to make a connection with what we have just said on image compression. So the idea is that, for example, the green image here can be represented as a combination of few columns of D, that is only the columns which corresponds to the non-zero elements of this second column of X that corresponds to the green dots. Okay. Just to give you a further idea of the roles of this factorization, let's consider an example given by image classification. So in this case, Y is given by a set of images. These are Zalando articles. So you have t-shirts, shoes, trousers, and so on. And so this is the computed, a computed dictionary that solves the dictionary learning problems. We will see, but it's a sort of solution. And as you can see, in each of these small image here corresponds to an atom, that is to a column of D. And as you can see, it is just a compressed representation of the redundant information contained in Y. I mean, you can recognize here maybe some t-shirts or shoes and so on. So it is a sort of compressed version of the data set. On the other hand, the role of X is that of clustering the data by selecting for each image contained in the data set the columns of D which are more significant in the representation. So regarding the model for solving the dictionary learning problem, we consider these very well used and in some sense a simple formulation of the dictionary learning problem. In fact, so we measure the approximation in the factorization using the squared of the Frobenius norm of Y minus D times X. So here again, Y is given, D and X are both unknowns, both optimization variables. So we want to minimize this residual function, in some sense. Variable are D and X, so these fat matrices. And they have to belong to these two sets, which define the feasible sets, the constraints, problem constraints. So omega is this set here that just impose that the columns, so the atoms, have norm 1. The set gamma depends on this parameter tau, and it is responsible for the sparsity in the matrix X. So here we use the zero norm of the zero norm that counts the number of non-zero elements of a vector in this case. So here we impose that each column of D has at most tau non-zero elements. Tau is a given sparsity threshold, so it is a further parameter that we have to set a priori together with K, so the number of atoms. So these problems, from an optimization point of view, poses several challenges. First of all, challenges are due to the presence of the zero norm here. It is a nasty function. It is no-smooth, non-convex, and brings a combinatorial flavor to the problem, but so badly that in fact the problem is NP-hard. But this is the not only difficulty in the problem. The problem, because in fact the problem is not convex, just because here in the objective we have this bilinear form here. So the problem is inherently non-convex. On the other hand, if you look at this special nonlinearity here in the residual, you can guess that in fact the proposed algorithms for solving this problem are alternating algorithms. That is, the problem is addressed by focusing on on one variable at a time. In fact, generally, algorithms for dictionary learning problem alternate a sparse coding step where D is fixed and the problem is solved with respect to X. Of course, in this case, the problem has to handle the sparsity constraints, so the zero norm. And in general, these steps is performed using the orthogonal matching pursuit, that is a very well-known greedy heuristic algorithms that handles the zero norm that works quite well. The other step in the alternating procedure is the dictionary update step. Here X is fixed and the problem is solved with respect to D. I have to say that most of the algorithms share the sparse coding step, but differ in the way the dictionary is updated. Here you have some very well-known algorithms in the literature. And I mean, a nice feature of these algorithms is that in practice they work, but from a mathematical point of view, we have to say that they suffers from the lack of convergence properties. I mean, these kind of methods works, but it's not possible to prove convergence results under general assumption. That's why when we approached the dictionary learning problem, we consider a different kind of alternating algorithms that belongs to the class of so-called PALM algorithms. So PALM algorithms are, PALM stands for Proximal Alternating Linearized Minimization approach. And as the name said, in practice, these are gradient type methods, which takes into account the constraints in performing proximal steps. We will see later on what I mean. So proximal or projection steps. So the first work on these approaches is this by Bolt, Sebak, and Teboul, who proposed this family of methods for a very general class of optimization problems. And then it was, these methods were applied to dictionary learning in other papers that you can see here. One of the main features of these approaches is that it can be proved that they converge to critical points of dictionary learning, and more generally to critical point of a very large class of non-convex and non-smooth problems. So the class of problems that PALMs address is the following, more generally. So this is the optimization problem. So the objective is made by a first term that involves all the variables, and this is a smooth terms. And we assume that the partial Lipschitz gradients, so the gradient with respect to x and y, are Lipschitz continuous. And I will denote from now on by L1 of x and L2 of y and L2 of x the Lipschitz constant. Then in the objective, there are other two terms, so for which we don't make any regularity assumption. They only have to be lower semi-continuous. F1, F2 in general are no smooth function, but they depend only on a block of variable. So F1 depend on x and F2 depend on y. These are extended value function. That means that they can take also plus infinite as a value, output value. And this is important because this includes the use here of indicator function. And the use of indicator function allows you to include constraints in the objective quite easily. So the idea of the PALM alternating procedure is the following. So at the general jth iteration, x is updated. So first performing a gradient step, so along the partial gradient with respect to x of h. And then the obtained point is, to this point, the proximal map is applied. And the proximal map takes into account the no smooth function f1. So we make a gradient step along considering the smooth function, and a proximal step take into account the no smooth function, in few words. What is important here is that the step size, alpha k alpha, is computed as the reciprocal of the Lipschitz constant. In the same way, when you update y, you perform the gradient step and then the proximal map using f2. And again, here, the step size is the reciprocal of the Lipschitz constant. Observe here that when you update y, you use the just updated value of x. I just want to recall you the definition of the proximal map, that is this one. And the proximal map is defined for a function f that just assumes to be lower semi-continuous. But what is important, at least for the talk, is that if f is an indicator function. An indicator function is a function that, for instance, the indicator function over omega is a function that that is 0 if the point where it is evaluated belongs to omega, and is plus infinity if it doesn't belongs to omega, just to recall. So if in the special case where f is an indicator function, the proximal map is nothing but the projection on the set omega. So this is what we need to know in the following. Just pay attention to the fact that omega here is not assumed to be convex. So, I mean, the projection might not be unique. So just keep in mind that this is a very, very general framework because we don't make any convexity assumption anywhere. Okay. So, as I said, PALM is very important because it generalized to the non-convex, non-smooth case, very well-known alternating technique which were proposed in previous works for specific problems. So problems, for example, where convexity was assumed and so on. But one of the most important outcome of this paper is that it provides a convergence proof receipt. And this is important because it allows to design new methods based in some sense on the same scheme with the same good convergence properties. Just want to make a note saying that PALM was proposed with constant step size, meaning that the step size alpha is given by this reciprocal of Lipschitz constant. It is not always possible to know the Lipschitz constants. It depends on the problem. So it is not always possible to use this constant step size. So generally, the computation of alpha is performed using a backtracking strategy. And it is important to observe that also in this case, the convergence properties of PALM still hold. But which is the drawback of these PALM methods? Of course, the drawback is that in practice, the convergence of these methods is very slow. And this is due to the fact that in practice, these are gradient type methods. And so we cannot expect so much. But I mean, from the theoretical point of view, they were really, really important. So this drawback is the reason why in the last few years, many accelerated versions of PALM have been proposed. So many of them use inertial step. And this means that in few words, I mean, during the update of the iterates, one takes into account not only of the previous iteration, but for example, a convex, a linear combination of the previous two iterations, so on. So I mean, the iteration proceeds taking inertial information in the progress of the iterations. So this is these are some proposals. We proposed a further variant that is called PALM, that is spectral PALM. We will see why. That in fact try to accelerate convergence using Barzilai-Borwein step size. We will see in a moment what they are. So what is important is that using the proof receipt of the first PALM work, one could prove that all these methods, all these variants enjoy the same convergence properties of the original PALM. And as a byproduct, all these methods, when applied to the dictionary learning problem, can be proved to be convergent. So let's see some details about the spectral PALM. So the alternating scheme, believe me, is the same as before. It doesn't seem, but it is the same. I mean, for example, here, if you update X, you see this is exactly the same formula as before. The only difference is in the way that the step size is computed. And this step size is computed starting from the so-called Barzilai-Borwein step size that I will describe in a moment. And so the step size alpha bar is computed starting from this and then checking if this condition is satisfied. This is nothing but an Hermigio type condition, is a sufficient decrease condition, is quite common in line search procedure. Here it is defined for C1 and C2, which are the function, Phi1, the one that involves only F1, and C2 involves only F2. But I mean, this is a standard line search procedure that is made in this case in each variable. So this means that this is the backtracking strategy starting from the Barzilai-Borwein step size, and analogously for the update in Y. Okay, so we start from this BB step size and reduce if necessary until this condition holds. So let's see, so the main ingredients of these algorithms, that is how these BB step sizes are defined. So BB step size due their names to the Barzilai-Borwein, who were those who proposed them for the first time in the solution of convex quadratic function, and then extended to the linear optimization problem by Redan. So the idea of these step sizes is that they are scalar that somehow contain in a nutshell, I would say, the second order information of the objective function. And how it is possible? So the idea is that if you want to update X, you would like, in principle, you would like to use information about the second derivatives of H, but it's too expensive to build this matrix. And so the idea is to approximate this matrix by a multiple of the identity. And how the scalar here in front of the identity has somehow the role of capturing the spectral information of the Hessian. That's why these step sizes are called spectral step sizes. And this is possible using a quasi-Newton framework, what is called quasi-Newton framework, where we define S that measure the difference between two consecutive iterates, G, the difference between two consecutive gradients, and then computing the step sizes that solves this minimization problem here. This corresponds to imposing the second equation to the approximate Hessian, for those of you who knows a bit of quasi-Newton procedure. But I mean, the fact that we compute this alpha BB solving these least squares problems enables to include some second order information in these scalars. The solution of, the form of these step sizes, BB1 and BB2, is explicit, so one can write them. So you just have to compute scalar products between these S and G. And of course, the same can be done in the variable Y, take into account that we take with us that's just computed X. So, I mean, the idea of using spectral information of the Hessian in a scalar is not new. Of course, it is very well, it's widely used in optimization. But here, the novelty is in the fact it is used in an alternating framework. And somehow, I mean, these step sizes takes into account the history of the alternating iteration. And so this is quite new. And what is new is that, that's all. I have another slide in between. Okay, so this is the idea of SPALM. Okay, so is PALM algorithms where the step sizes are spectral step sizes. So what happens if we apply PALM and SPALM to the dictionary learning problem? As I said, we can rewrite the problem. You remember that X had to belong to the set gamma and D to the set omega. So we can rewrite the optimization problem in this way using this indicator function that will be F1, F2 in the previous formulation, while this first term here is the smooth term. So this is the form of a Palm type update. So a gradient step is performed along the partial gradient with respect to x, and then the proximal map is applied. So in this case, the proximal map is a projection, because here we have indicator function, and the projection over the set that is defined using the zero norm is the so-called, very quite used, hard thresholding operator, that in fact takes the tau largest components of each column of x and put the others to equal to 0. Then D is updated, again, moving along the partial gradient with respect to D. And here we have the projection over the matrices with the with one norm columns. So these are the form of the gradient, and the form of the step sizes depends on the method used. So if we use Palm, and so we need to compute the reciprocal of the Lipschitz constant, in this case, they can be computed, they are known, and have this form. If we use S-Palm, so we compute the Barzilai-Borwein step sizes, these are the forms of the step sizes in X and D. And as you can see, they have they can be computed here. These are scalar product with respect to the trace product in, of course, in the metric space. So here, again, this is just the easy way to computing the projection over the set of matrices with one norm columns. So this is what I wanted to say here. We could prove a result that relates the Barzilai-Borwein step size with the spectrum of the Hessian, and in particular with the Lipschitz constant. So we could prove that the Barzilai-Borwein step sizes are always larger than the reciprocal of the Lipschitz constant. And this is, in some sense, a well-known property of these methods, and so we could of these step sizes, and so we could prove that this holds also when working in an alternating fashion. And moreover, we provide an upper bound that was not known in the literatures, because here what we have is that in fact the second derivatives of H are just positive semi-definite, not positive definite. But as you can see here, there is a relationship between the spectrum of the second order derivatives and the spectral step sizes, and the fact that they are larger than the reciprocal of the Lipschitz constants means that we hope to make a larger step along the gradient using this step than using a conservative step sizes given by the reciprocal of the Lipschitz constants. So the hope is to accelerate convergence by using second order information and performing larger steps. So let's see some experiments, and these experiments are related to an image classification task. So here for the moment, let's consider grayscale images. So we have a database of images of NP persons or object in NE expression, so view angle, illumination, expression, and so on. So the idea is to classify a further image by assigning to a specific label. So for example, I have another article here. I want to, that is not in the data set. I want to say if it is a t-shirt or shoes and so on. So these are the databases that we considered. So the question is where the dictionary learning problem appear in this framework. So image classification can be solved alternating a training phase and a testing phase. In the training phase, so given a data set Y, the first step is to solve a dictionary learning problem. That means fixed K and tau, which are the two parameters that we need to set for the dictionary learning problem. First, we find a solution. So we find X hat and D hat, which gives an approximate factorization, the product of the data set Y. And so here we can apply one of our favorite PALM methods. So PALM, SPALM, whatever you want. Once you have computed X hat and D hat, you compute the so-called classifier. That is a matrix W that solves this least squares problem, where C is a matrix that contains the labels of each training image. So it is a matrix of 0 and 1 values. So once you have the classifier, you can classify an image U that is not in the data set. And how you do it? So you first compute the sparse representation of X. That means that you solve this problem where D hat was previously computed, no, in the step 1 here. Once you have the sparse representation, you compute L applying the classifier, and then you classify U as, for example, the person P hat that gives you the maximum value of L. And this is because L of P can be interpreted as the probability that X hat is the sparse representation of the person P. So you want to maximize, of course, the probability. So now what we do is to solve some image classification problems where we change the way we solve the dictionary learning problem. And in some sense, we want to evaluate the impact in the end, so in the image classification performance, varying the solver in the dictionary learning phase. So these are some information about the experiments. And regarding the solver for the DL problem, we compared SPALM, where we alternate the BB. So we use BB1 and BB2 alternated. PALM with exact Lipschitz constant and the inertial variance, both using the exact Lipschitz constant and using backtracking. So here, what we do is to measure the so-called classification rate. That is the percentage of correctly classified persons or objects over the total number of test images. So, for example, if you look at the first data set, you can see that changing the solver in the training phase doesn't make any changes. So both gives the same successful classification rates. The same is true for these, would say, for these data sets. These are still phases where you see the percentage are very similar. Something changed when you use these two other data sets, so the handwritten digits and the Zalando articles. And as you can see here, when you use spectral palm or inertial variant, you gain in classification rates. So, but let's see the price of gaining in classification rate. So in these plots, you have the residual function with respect to CPU time. As you can see, I mean, if you look at the orange curve, that is the spectral approach, and the inertial palm with backtrack, which were those giving the best classification rate. As you can see, spectral palm is always the fastest method that finds a solution in all, I would say, in all examples, and in particular also in these two examples where we also have a gain in classification rate. And so it is faster than the inertial palm with backtrack, and it takes the same time more or less than the palm, the original palm version, but recall you that we gain a lot in classification rate with respect to this. So with the same CPU time, we gain in classification rate. So since it's not easy to compare methods, these methods, I mean, measuring the classification rates, because it is something that is made a posteriori after the testing phase, we now focus on the comparison between the methods only in the solution of the dictionary learning problem. So without taking into account classification performance. So we run the four solvers using this stopping criterion, because I forgot to tell, but in the previous runs, we only perform the 50 iterations for all the methods. So here, this is a stopping criterion. And as you can see, I mean, this accuracy requirement is achieved by spectral palm in less time than for the other methods in all cases. And also, if you can see from these nice curves here, I mean, I don't know if you can appreciate, but what I see in these curves is that the second order injection helps in accelerating convergence. So here we can see that second order really helped in achieving a solution in less time. So now just a few words on a tensor approach that we propose for solving the dictionary learning problem. And first of all, I want just to give you the motivation of considering a tensor formulation of the problem instead of a matrix formulation as we discussed so far. So the main point is that data set of images are naturally can be naturally represented by a tensor. So for example, here you have images of different person, different expression, and so, for example, you can represent this data set by a tensor, where here the first two dimensions are the actual picture size, and these are the number of expression and number of person. Okay, so naturally the data set is a fourth order tensor. This is also true for other kinds of data sets which are multidimensional. In fact, for example, if you have RGB images, you will have a fifth order tensor to represent the data sets, or if you have hyperspectral images and so on. So the idea is to keep this somehow inherent structure of the database in order with the aim of preserving data structures and feature heterogeneity in the data. So what we wanted to focus on is on this tensor formulation. This is exactly the same as before, same problem, but now here y is kept in this tensor form. This is an example, of course, of a fourth order tensor, but can be generalized to any order. And here, this is a special product between tensors that allows to rewrite the problem equivalently to the matrix case, and denotes the M to N mode product. Here, this number here, this pedix here, denotes a sort of reshaping of the tensor in order to rewrite the same constraints that we have just seen for the matrix case. So this is a general tensor formulation, and what we propose to do for solving the problem is to decompose the dictionary that in its tensor fashion as a product of matrices, in this case, using the so-called tensor train decomposition. So in this case, D is written as this product here, where G1, G2, and G3 are the so-called TT cores. And as you can see, the dimension of these cores depends on these parameters R1 and R2, which are the TT ranks, and can be chosen in different way. I mean, they can be chosen such that the dimension of the products corresponds to the dimension of D, or can be cleverly reduced with respect to the full dimension in order to reduce the memory usage. I mean, storing G1, G2, and G3 will be less memory consuming than storing the tensor D. In this sense, we will use a sort of truncated tensor train decomposition. It's important to know that now the constraints on X is the same, where X is again a reshaped version of X, calligraphic. G3 inherits the constraints from the dictionary learning formulation. G1 and G2 have to be orthonormal. And so we impose these constraints in this way. So theta is the set of orthonormal matrices. So I don't want to go into details, but you can imagine that once we have this problem that now depends on 4 variable blocks, one can rewrite the problem in a palm fashion, let's say. And so one can, so if we include the constraints in the objective, we can now apply a palm method or a variant of palm method, and we could provide explicit form for the Lipschitz constant that take into account the orthonormality of G1 and G2, and moreover we could prove that if we apply a palm type method to the solution of this tensor train formulation of the dictionary learning problem, the method converges to stationary point. This was important in the tensor literature because this was one of the first, convergent tensor-based algorithm for the dictionary learning. So this is just the updating scheme, so you can understand that it can be easily generalized. I mean, the Palm framework just updating each block one at a time. Here, the novelty here is that we have to project on the set of orthonormal matrices. So only a few experiments. I promise to be quick. So here we compare Palm and as Palm in matrix and tensor fashion, applied to the 2 different problems. As you can see here from this plot is that the spectral palm gives a better classification performance in general, in fewer iteration. But if you compare, the 2 formulation, the matrix and the TT formulation, we have to admit that here we don't see any advantages, at least from the classification percentage point of view. Because these are very, very close, no? The lines, the curves. But what we can gain is something related to the memory, because if we cleverly use a truncated strategies, we can show that using much less information on D. So if we, for example, reduce the rank, we don't pay in classification performance. So we can achieve the same classification performance as using a full TT decomposition using less memory. So the advantages of using, so far we found that the advantages of using this TT formulation comes from the fact that one can save memory. So this is another experiment. This is the data set with colored images, so with the colored ducks. And here in this data set, now here the tensor is a 5th order tensor. Here we found an advantages of using S-palm, these 2 lines, so the red and the orange. But the S-palm and the TT formulation gave the best performance. So the combination of both the TT and the spectral steps gave the best performance. So concluding, so we proposed a new variant of Palm that uses spectral step sizes, and this was a novelty in this framework. And the hope was that of helping the convergence speed using second order information in the step sizes. We proposed a tensor train formulation for the dictionary learning problems, And we applied our method, but also all the other methods, Palm methods, to this formulation, and proved that these keep the convergence properties of the matrix counterpart. And that's all. I think you can find all the details on archive. Thank you very much.
Thank you, Margherita, for the nice talk. Do we have any questions? Jemima, please.
Yeah, so you, in both methods, you have this choice of parameter, either K or the ranks for your training. How do you select these? Is there a good way to do it, or is it kind of your
sorry, I didn't understand which parameter.
So for the tensor example, you have the choice of the R1 and the R2.
R1 and the TT ranks, you mean?
Yeah, exactly, yeah.
I mean, the truth is that we tried by, we made just a count of the memory of occupancy. So this is the number of elements contained in D and X of the memory for the matrix approach. In the TT approach, we have this, okay, and so we could find, for example, that the memory used for the TT is below the memory used for the matrix version when R2 is below this quantity here. Mm-hmm. Okay, so first of all, above we don't gain. I mean, we use more memory than in the matrix case, and so the idea was just checking what we can say. For example, here in this case, I mean, for all this value of the ranks, we save memory, but we can see that we can use, for example, 70, R2 equal to 70, just to obtain the same classification performance. So it doesn't make any sense to use more memory. I mean, we don't have an adaptive rule, for example, for choosing these ranks, and so we just made experiments to see what we could gain, but nothing more sophisticated, I'm afraid.
You could do something more sophisticated, or is it just a matter of trying to do?
I mean, I think yes. But then the approach would be different. Mm-hmm. So, for example, one could do something using manifold optimization. So, so I think that using optimization algorithms using geometrical properties of the TT decomposition, then I think we could do something. But I mean, for the approach proposed so far, I think we cannot do much more than this.
Thank you.
Any other question? So from Zoom?
I don't think so.
Okay, I actually have a question. So like in your tensor approach, you have some ingredients like the low rank truncation and the orthogonality of certain matrices, certain, like, I don't remember exactly the name, like G1 and G2 maybe, that you don't have in a matrix setting. That actually I think it may make sense, for instance, to have a low rank truncation of your D and X. So like having low rank and sparse dictionary and representation X.
I mean,
because you usually, as you said, you usually choose a large K. So like I can see having a low rank D in that case, at least numerically, but still having a sparse X. So like have the same basic representation, but with a smaller K. So like running your method with a certain K, possibly large, and then see if you still have some redundancy in terms of like rank of the dictionary more than the sparsity of X.
I don't know. It's true is that this is a sort of way of imposing a low rank in the dictionary in this way, but other formulation are possible. I mean, if we insist on this formulation here, this is what we can do. Yes, for sure, the number of columns on D, in some sense, has an impact on the compression and so on the sparsity of the representation. So for sure, these things are related. So yes, one could try to see what happens.
Yeah,
and yes, but I think
yeah, to imposing an orthogonal structure on D.
I mean, yes, it's possible. I mean, if one, but as I said before, this would mean some sense to change the problem formulation. I mean, we started from this and trying to find a way to solve it. There are different formulation of the problem, so you can impose constraints in different ways. So, for example, also you can use different things from the zero norm or something like that, imposing a rank, and so I mean. Yes, we could change the model for the dictionary learning problem,
Okay.
that's for sure, and then use corresponding suitable techniques. But I would see this as a change in the model formulation. But yes, for sure.
Yeah. Okay.
Good. Thanks.
I think we are done for today. So I'd like to thank Margherita once again, and all the other speakers. And see you in Bologna.